The orientation of the grounding terminal on electrical receptacles, whether up or down, is a topic of discussion among electricians. While personal preference and specific circumstances can play a role, there are code considerations, practical benefits, and potential drawbacks to both approaches. Installing receptacles with the ground up adheres to the National Electrical Code, specifically Article 406.3, which mandates that the grounding terminal be located at the top of the receptacle. This configuration ensures proper grounding of the protective earth wire, typically the green or bare copper wire. Placing the ground up simplifies the identification and connection of the grounding wire, as it consistently occupies the uppermost position. This consistency promotes a more reliable grounding connection, which is crucial for electrical safety. Adherence to electrical codes and safety standards is paramount, and installing receptacles with the ground up ensures compliance. While the NEC doesn't explicitly prohibit installing receptacles with the ground down, the language in Article 406.3 implies a preference for the ground-up orientation. Some electricians favor the ground-down orientation because it can simplify wire bending, particularly in confined spaces or when working with thicker gauge wires. Bending the grounding wire to connect to the bottom terminal may prove easier in certain scenarios. Provided the grounding connection is made correctly and securely, installing receptacles with the ground down does not necessarily violate electrical codes. However, it's important to note that some inspectors may interpret Article 406.3 as a requirement for the ground-up orientation. Additional factors to consider include the orientation of the receptacle box, for example, whether it's vertical or horizontal, which can influence the optimal placement of the ground terminal. Outlet covers sometimes feature a notch or opening at the top to accommodate the grounding screw. Installing the receptacle with the ground up aligns the screw with this opening, potentially simplifying installation. Ultimately, the preferred orientation may depend on individual preferences, working conditions, and the design of the receptacle itself. A general recommendation is to install receptacles with the ground up to ensure code compliance and proper grounding. However, the ground-down orientation may be acceptable in situations where wire bending is a significant concern. To delve deeper into the technical aspects, we can explore the role of the grounding conductor in an electrical system. The grounding conductor provides a low impedance path for fault current to return to the source. This low impedance path facilitates the rapid tripping of a circuit breaker or fuse, interrupting the flow of electricity and preventing electrical shock or fire hazards. When a fault occurs, such as a short circuit between a live conductor and a grounded metal enclosure, the fault current flows through the grounding conductor back to the source. This high current flow causes the circuit breaker or fuse to trip, disconnecting the circuit and preventing further damage or injury. The size of the grounding conductor is determined by the size of the ungrounded conductors in the circuit, as specified in the National Electrical Code Table 250.122. It's crucial to use the correct size grounding conductor to ensure adequate fault current carrying capacity. The grounding conductor must be securely connected to the grounding electrode system, which typically consists of a ground rod, ground plate, or metal water pipe. The grounding electrode system provides a connection to the earth, which helps to stabilize the voltage of the electrical system and provide a reference point for grounding. The resistance of the grounding electrode system should be as low as possible, ideally 25 ohms or less, as specified in the National Electrical Code Section 250.53. A low resistance grounding electrode system ensures that fault current can flow easily to the earth, facilitating the rapid tripping of a circuit breaker or fuse. Ground fault circuit interrupters, also known as GFCIs, are another important safety device used in electrical systems. GFCIs are designed to detect small imbalances in current between hot and neutral conductors, which can indicate a ground fault. When a GFCI detects a ground fault, it quickly trips the circuit, preventing electrical shock. GFCIs are typically required in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. They are particularly effective in protecting against line-to-ground faults, where current flows from a live conductor to ground through a person's body. Arc fault circuit interrupters, or AFSIs, are designed to protect against arc faults, which are dangerous electrical conditions that can cause fires. Arc faults occur when electricity jumps between two conductors, creating a high-temperature arc. These arcs can ignite nearby flammable materials, leading to a fire. ASIs are designed to detect the unique characteristics of arc faults and quickly trip the circuit, preventing a fire. They are typically required in bedroom circuits and other areas where there is a high risk of fire. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. An overload occurs when too much current flows through a circuit, causing the wires to overheat. A short circuit occurs when there is a direct connection between two conductors, resulting in a very high current flow. Circuit breakers are receptacle devices that trip when the current exceeds their rated amperage. Fuses are one-time use devices that melt and break the circuit when the current exceeds their rated amperage. The selection of the correct size circuit breaker or fuse is critical to protect the electrical circuit from overloads and short circuits. The National Electrical Code provides guidelines for selecting the appropriate overcurrent protection device based on the ampacity of the conductors in the circuit. Proper wiring techniques are essential for ensuring the safety and reliability of electrical installations. All electrical connections should be made inside approved electrical boxes. These boxes provide a safe enclosure for the connections and protect them from damage. Wire connectors, such as wire nuts or terminal strips, should be used to make secure and reliable connections between wires. The connections should be tightened properly to ensure good electrical contact. Wires should be properly supported and protected from physical damage. They should be routed away from sharp edges and other potential hazards. The National Electrical Code provides detailed requirements for wiring methods, including the types of wiring allowed, the methods of support, and the protection required. Regular inspection and maintenance of electrical systems are essential for ensuring their continued safety and reliability. Electrical systems should be inspected periodically by a qualified electrician to identify any potential problems. Loose connections, damaged wiring, and malfunctioning devices should be repaired or replaced promptly. Grounding systems should be tested to ensure that they are functioning properly. Overcurrent protection devices should be tested to verify that they trip at their rated amperage. By following these guidelines, it is possible to ensure the safety and reliability of electrical installations and protect people and property from electrical hazards. The National Electrical Code, or NEC, serves as the cornerstone of electrical safety in the United States. Published by the National Fire Protection Association, it's a comprehensive set of standards and guidelines designed to ensure the safe installation and maintenance of electrical systems. Understanding and adhering to the NEC is crucial for electricians, contractors, and anyone involved in electrical work. The NEC is updated every 3 years to reflect the latest technological advancements and safety practices. These revisions often incorporate new requirements, address emerging hazards, and clarify existing rules. Staying current with the latest edition of the NEC is essential for ensuring compliance and promoting electrical safety. The NEC covers a wide range of topics, including wiring methods, grounding, overcurrent protection, equipment installation, and special occupancies. It provides detailed requirements for conductors, cables, raceways, enclosures, and other electrical components. The code also addresses specific applications such as residential wiring, commercial wiring, industrial wiring, and hazardous locations. One of the key principles of the NEC is to protect people and property from electrical hazards such as electric shock, fire, and explosions. The code establishes minimum safety standards for electrical installations to minimize these risks. It also emphasizes the importance of proper grounding, overcurrent protection, and wiring methods. The NEC is not a design manual, but rather a set of minimum requirements. Electrical designers and installers may choose to exceed these requirements to enhance safety or improve performance. However, they must never fall below the minimum standards set forth in the NEC. Enforcement of the NEC is typically the responsibility of local jurisdictions such as cities, counties, or states. These jurisdictions may adopt the NEC as law or incorporate it into their building codes. Electrical inspectors are responsible for ensuring that electrical installations comply with the NEC and other applicable regulations. The NEC is a complex and technical document, and it can be challenging to interpret and apply. Therefore, it's important to consult with qualified electrical professionals who have a thorough understanding of the code. These professionals can provide guidance on proper installation techniques, code compliance issues, and other electrical safety matters. The NEC is constantly evolving to address new challenges and improve electrical safety. By staying informed about the latest revisions and seeking guidance from qualified professionals, it's possible to ensure that electrical installations are safe, reliable, and compliant with applicable codes and standards. The importance of proper grounding cannot be overstated when it comes to electrical safety. Grounding provides a low impedance path for fault current to return to the source, which helps to protect people and equipment from electrical shock and damage. A properly grounded electrical system helps to stabilize voltage, reduce electrical noise, and prevent the buildup of static electricity. Grounding also provides a reference point for electrical measurements, making it easier to troubleshoot and maintain electrical equipment. The grounding system typically consists of a grounding electrode, such as a ground rod or ground plate, and a grounding conductor, which connects the electrical system to the grounding electrode. The grounding electrode should be installed in contact with the earth and should have a low resistance to ground. The grounding conductor should be sized appropriately for the electrical system and should be securely connected to the grounding electrode and the electrical equipment. There are different types of grounding systems, including equipment grounding and system grounding. Equipment grounding provides a path for fault current to return to the source in the event of a fault in the electrical equipment. System grounding provides a reference point for the electrical system and helps to stabilize voltage. The National Electrical Code provides detailed requirements for grounding electrical systems. These requirements cover the size and type of grounding conductors, the installation of grounding electrodes, and the bonding of metal enclosures. Proper grounding is essential for ensuring the safety and reliability of electrical systems. It helps to protect people and equipment from electrical hazards and provides a stable and reliable electrical supply.